Hi everyone, my name is Naved Haq, and this is my Lab 2 report for Physics 2211 on projectile motion. In this experiment, I analyzed how a projectile moves under gravity, and compared real-world motion from video tracking to theoretical motion predicted by computational models that I built in GlowScript vPython. The goal of this lab was to study the motion of a projectile and compare the experimental data to theoretical models. I recorded a paper ball being tossed and analyzed its motion in Tracker to get position and velocity data. Then I created two models in GlowScript, one with gravity only and another with gravity plus air resistance. Both were based on Newton's second law, which is force equals mass times acceleration, where gravity and drag are the two main forces involved in this experiment. By comparing the models, I could see how the model incorporating air resistance matched the actual data closer. For the experiment, the system was the paper ball which I threw, and everything else like the air, me, and the environment were the surroundings. We chose to use a paper ball because it would experience more visible drag due to its uneven and irregular shape. I measured the mass of the paper ball and then used a ruler in the video to set the scale in Tracker. The setup was simple. I simply tossed the paper ball upwards, recorded its motion from the side, and then in Tracker I could collect position data frame by frame. This gave me X and Y position data that I needed for modeling, which I inputted into Excel. Both models used in this experiment came from Newton's second law. Again, F equals ma. Model 1, the gravity-only model, assumed that the only force acting is weight, F equals mg, which gives a perfect parabolic path. Model 2 adds a drag force, negative bv squared, which always points opposite to motion and depends on the square of velocity. We compared these two theoretical models to the actual data to understand how air resistance affects trajectory, velocity, and range. The code that I used is featured on the right, and you can see the link up top. I wrote my program based on the provided GlowScript starter code. I defined the ball's mass, position, and velocity, and then used a time loop, which you can see on the right, to update its motion step by step with the momentum principle. Velocity equals old velocity plus force over mass times delta t, and position equals old position plus velocity times delta t. I ran the simulation for 0.77 seconds, matching the video's length. I then adjusted the drag coefficient b using trial and error until the simulation closely matched my Tracker data. Finally, I plotted both model results against my experimental data to compare trajectories. And you can see that graph on the top right. The gravity-only model didn't match the real motion very well. It predicted constant acceleration with no slowing. The model with drag matched the Tracker data much better, especially after the ball peaked and started falling. Some potential sources of error are clicking inaccuracies in Tracker and the process of guessing the b-value. Neither model reached the terminal velocity because the motion was too short for the forces to balance in the case of the model with drag, or there was no other force to balance in the no drag model. To find terminal velocity, I could drop a lighter, high drag object, such as a flat sheet of paper, from a taller height until its velocity stops increasing. If the same object were thrown straight up with the same initial speed, it would take longer to reach the ground. That's because it first slows to zero velocity at the top, then accelerates back down. Using kinematics without drag, the total time is 2 times v initial over g, which is longer than the time for just the downward motion. With air resistance, the total time is still longer overall, though the upward part will be slightly shorter because drag acts against the motion both ways. In conclusion, the gravity plus drag model best represented the real motion of the paper ball. Air resistance clearly reduces the projectile's range and maximum height, and the gravity-only model didn't account for all forces present. The comparison of graphs and data showed that including drag gives a far more accurate prediction of the model. Thank you for watching.